Instead of narrowed, it's opened up a little bit. You guys are pretty good. I don't imagine anybody's going to want the full 3 hours, but I guess that does make it available for 3 hours if you wanted to.
Oh, wow. That's a lot.
Yeah, I don't think you want it 3 hours. The only reason I'm opening the test window is because I want to participate in something that's happening at 2 o'clock, yeah.
Mhm.
And so I have somebody coming in to cover me about 1:30. So we're going to be in the same place as we were last time. And so about 1:30, I'm going to be slipping out. She's going to be slipping in. So if you want to go to the same event I'm going to at 2 o'clock, then that means you need to start your exam a little bit early. So that's kind of how that works. I don't know. Yes, you can come in later than noon, yeah. Definitely. But probably the latest you want to come in is 1, you know.
Yeah.
So, yeah, I figured we were on the same track with that. Okay?
But we can come in earlier now, though, too. We can
So
come in at noon.
yes, you can come in at noon. You can come in at 12:30, you can come in at 12:45. But I think by 1 you should be kind of started. Yeah, these tests are taking you guys maybe 45 minutes to an hour and a half. So even though you have full 2 hours to take them. And you can have full 2 hours to take them. You can have 3 hours this time if you want. So it's a thought. That whole assessment thing, I'd just rather not have to assess. I'd rather just, you know, but. Okay, but yeah, I think this is a great event. So I'm excited. It's going to be in the cafeteria. I'm thinking about snacks. What do you think? I don't know. Popcorn, what's appropriate for a planetary astrophysicist? I don't know. Some what? Moon pies. Oh, I love it. That's really good. But see, he won't be here. He'll kind of be here. But maybe we should eat moon pies in front of him. Okay. Well, today's lecture actually probably will not take the full time. So that all works, right? It all comes out in the end. And I've already told you I kind of like wrapping around and finishing up with part 3
All the way back.
to kind of remind you of the stuff we talked about earlier. Some of part 3 will be reminiscent of actually part 2 when we talked about empirical formulas and molecular formulas and going back and forth between weight percent and empirical formulas. Okay, that was part 2. That's maybe going to ring some bells here. All right, so remember what an empirical formula is? It's kind of like that distilled sort of nuts and bolts formula of a compound. Sometimes empirical formulas can be kind of scaled up to the molecular formula, okay? So remember kind of the difference between empirical formula and molecular formula. So what this says is basically we can determine the empirical formula of a compound using, looking at its, this is what it looks like. Actually, if you're a picture person, you're taking a CXHY, okay, some sort of hydrocarbon. You're burning it. You're going to add oxygen. And you're going to actually, when it talks about combustion products, we're actually mostly going to focus on when your combustion products are going to be carbon dioxide, CO2, plus H2O. Okay? So bottom line, this sort of analysis is where you can come up with what is the empirical formula of that compound that you burned. Okay? The other broad type of compound is going to be one that has carbon, hydrogen, and oxygen. So it's going to be CXHYOZ, okay, plus oxygen. Gives you the same thing, carbon dioxide gas and actually water gas. So basically, we're going to study these two, the masses of those two things, and kind of backtrack to what the empirical formula is. Okay, it's a type of problem, combustion analysis. So combustion just in general is combining the other, one reactant is oxygen, the other reactant is what the reactant is. And on the product side, basically, all of your products basically have oxygen as part of them. The example I gave you was CO2 and H2O, right? All right. But I'm actually, for your homework, you're going to see that we can broaden out this this process. Okay, so here we go. Oops, I was going to go back. So this is the nuts and bolts of what I put up a minute ago, where you have, this is called a hydrocarbon. Okay, does it look like a hydrocarbon? Hydrocarbon, okay, burning with oxygen. Now actually, algebraically, you can knock out their stoichiometric coefficients, and this is the relationship of the 4 coefficients, what they have with each other. We're not going to balance equations that way, but there's a thought. You can solve them algebraically. The other type of problem we're going to do in lecture is where, again, you have basically a hydrocarbon with oxygen, okay? And you get the same thing. You get hydrocarbon with oxygen, you get carbon dioxide and water. Again, those are the stoichiometric coefficients, just to kind of show you for kicks that you can. But to me, you basically have 2 unknowns and 1 equation. I don't know. But we're not solving for the stoichiometric coefficients. But we are solving for the empirical formula of the compound. That's what we're after. So here's the deal. If you look back at either one of those equations, do you see where all of the carbon in your CHY ends up as carbon in your carbon dioxide? That's the only place the carbon can go. Any carbon in your carbon dioxide, where'd it come from? From your sample, your hydrocarbon. Similarly, okay, with regard to the hydrogen, if you kind of look back and forth between the reactants and the products, okay, your product burning either a hydrocarbon or a hydrocarbon with water, it forms carbon dioxide and hydrocarbon with oxygen. It gives you carbon dioxide and water, and your water, your H2O, those hydrogens came from the sample that you burned. Okay? So we're going to actually count on that. That's important to working these problems. If you get past that, then these problems kind of fall into place. We'll see. So in a combustion analysis, I'm going to show you an example here in a minute, but a little video. But basically, they have a cool sort of gizmo to weigh the carbon dioxide that's produced. What's the mass of the CO2 gas? Okay, and then we backtrack to moles of CO2 gas. So moles of CO2 gas, and then moles of carbon, and then moles of carbon came from the sample that we burned. Okay, similarly, we get to our hydrogen in the thing we burned from our water, basically. If there is oxygen, and we're going to do 2 problems this afternoon, the second problem actually is burning something that has carbon, hydrogen, and oxygen. If there's oxygen there, then I'll show you the example of how we have to get to oxygen. The problem with oxygen is basically if you have, CHYOZ plus O2, I mean, you're adding oxygen from, either you're piping it in or it's coming from the room or something like that. So we actually backtrack and get the oxygen by difference. I'll kind of show you that. All right, so here's a little video. You know what? I don't think yeah, I did. All right. So this is actually a still image, basically, of the video you just saw. And they went ahead and this right here, this is your molecule that you're burning. The black circles, the black balls are carbon atoms. The white balls are hydrogen atoms, and the red ball is an oxygen atom. Okay, so this is actually a hydrocarbon with oxygen. We burn it with oxygen, and we get water and carbon dioxide, and excess oxygen is spitting out the tube there. Okay, so then you just weigh those back. So let's work a problem. So as you might imagine, I think these kind of lend themselves to a picture. It's typically what I do. So here is my this is the stuff I'm going to put in the furnace. Okay, and I'm just going to call this CXHY. Okay, it says a sample of hydrocarbon, okay, was completely combusted with oxygen. So I'm going to put plus O2, okay, and actually we can if we want to. In these sort of problems, we can put the word excess if you want to. Sometimes the problem says it, but there's excess O2. And we've been saying the thing that forms is, of course, going to be CO2. I've been putting CO2 first. CO2 gas and H2O gas that can be weighed back again. That's it. So let's go ahead and put some numbers in. The thing that we're burning, the hydrocarbon is 0.188 grams. 0.1888, excuse me, 3/8 grams. Then it says that after they weighed back the cartridges, they saw that the CO2 mass was 0.6260 grams. 6260 grams, carbon dioxide, and the water was 0.1602 grams. So again, kind of the crux of how we're going to work this is all of these carbon atoms, okay, came or ended up as carbon atoms there, and all of these hydrogen atoms ended up as hydrogen atoms there. That's it. So we're supposed to knock out the empirical formula of compound. I was cold earlier, now getting up. All right. So we're gonna look at carbon separately, and we're gonna look at hydrogen separately, and then kind of bring them together. So focusing on carbon first, we need to use the mass of the CO2. Okay, so the mass of the CO2 was 0.6260 grams CO2. Bottom line, what I'm trying to get to is moles of carbon. So, okay, so we can use the molar mass of carbon, which I didn't write here, which you're going to have to write. Molar mass of carbon is like that. Was it 44.01? Okay. So calculate the molar mass of CO2, carbon dioxide, excuse me. So use the molar mass of carbon dioxide, 1 mole of CO2 over 44.01 grams of CO2. Grams of CO2 cancel. We're left with moles of CO2. Moles of carbon in moles of CO2, it's a 1-to-1, actually. Okay? So actually the next ratio is simply 1 mole of carbon in 1 mole of CO2. And then we have moles of carbon. And we're done. We're done with that step. Looks like we need to round to 4 significant figures. And I'll show you why I'm going to do this in a minute. Because this might be reminiscent of when we did the weight percent, given weight percent of each element, getting to an empirical formula. But I kind of like the column thing. So actually, this is usually when I work these, what they end up looking like. So I'm going to go ahead and write down relative moles of each, carbon and hydrogen. So we got carbon from carbon dioxide, moles of carbon and carbon dioxide that came from the thing we burned is 0.01422 moles. Cool. Now we're going to turn to our water and knock out moles of hydrogen. So the mass of the water from the original problem was 0.1602 grams of H2O. Again, you're going to have to show the molar mass of water, but I bet you maybe know it's 18.02 grams per mole. Okay, so now we use the molar mass of water. 1 mole of H2O per 18.02 grams of H2O. Grams of H2O cancel. We're left with moles of H2O. Now, this is a very common mistake. I've made this mistake. Okay? We need to go to moles of hydrogen atoms, moles of hydrogen atoms. How many moles of hydrogen atoms are there in 1 mole of water?
2.
2. So the next thing is actually 2 moles of hydrogen over 1 mole of H2O. I'll go ahead and tell myself. So now we're left with units of moles of hydrogen atoms, moles of hydrogen that must have come from the thing that we burned. So rounded to 4 sig figs. I got 0.01778 moles of hydrogen, relatively speaking. I don't know if this is ringing any bells, but when we talked about taking weight percents and coming up with an empirical formula there, like we're trying to come up with an empirical formula here, I said basically you can take these numbers and kind of substitute them in for relative amounts. So we have, 0.01422 moles of carbon for every 0.01778 moles of hydrogen. Of course, we don't do that because they need to be whole numbers. So this is where kind of like if I have a table, what I did last time is I basically divided by the smallest number, and the smallest number is this one, the 0.01422. So I'm going to divide both by 0.01422. Okay, if you have more than one thing that you're trying to, that's in your formula, this is when this, I think, table really helps. So of course, if I take this number divided by itself, I get 1. I'll go ahead and put 1.00. I brought a calculator here. If I take 0.01778 and divide it by 0.01422,
125.
ah, good. This is a good example. I get 1.25. Thank you.
Yep.
1.25. Now again, I'm reminding you one of the things that we talked about in part 2. If you get a quartersies like this, okay, we need to go ahead. We can't just round it. We got to fix it. Okay, so that's why I make one more column and I multiply everything by 4. So then this becomes a 4.00, and 1.25 times 4 is 5.00. Okay. So then we're ready to go ahead, and here in a minute for our answer slides, you're going to see it is C4H5. Final answer. But just like I did before, you're going to see here in a minute where you don't have to do a table. You can just kind of do it logically, find your way through it. So this is kind of what we did last time. If you go ahead and recognize with regard to carbon, we have 1.25 moles of hydrogen for 1 mole of carbon. This is an alternative way of coming up with the relative moles of 4 and 5, or 5 and 4. And then you would need to recognize that don't round something that looks like a quarter. Don't round something that looks like a half. Don't round something that looks like 3/4. Don't round something that looks like a third or 2/3. Okay? All right, so we can scale that up to, that's approximately equal to 5 moles of hydrogen for every 4 moles of carbon. Again, just kind of multiplying the numerator and the denominator through by, again, 4. So either way. Yes?
Up top, is that supposed to be 0.01787778?
Yeah.
Probably. Did I miss that? Yep. Thank you. That number, that first 8 should be a 7. Very good. Better? Any questions about that? So you get the same. Okay. Kind of straightforward. That kind of works for you. Okay. So the second problem I want to do actually is when you burn something that has oxygen in it. And it's confounded because actually you have oxygen in the hydrocarbon with oxygen that you're burning, and you also have it in the other reactant, oxygen. And it's going to end up, unfortunately, in your carbon dioxide and your water. Both have oxygen. You're like, I can't win, and you're right. Okay, so we're going to get it by difference. And if we're going to get it by difference, by mass difference, then actually we're going to have to, once we have this, moles of carbon and hydrogen, we're actually going to go ahead and take that to grams. Okay, so we're going to have an extra step. Once we have grams of these two things, we can actually go ahead by difference, subtract that from our original sample that we burned and get the oxygen. Okay, so that's kind of what you're going to see coming up here. So let's see. Let's just, well, I'll skip the picture, but I will go ahead and write the numbers underneath. You guys don't have that, do you? So in this case, we are burning something that contains not only carbon and hydrogen, but also contains oxygen. So there will be an extra step. The mass of the thing that we're burning is 0.236 grams. Okay. It's completely reacted, so that means we had O2 is not limited. The mass of the CO2 is 0.421 grams. The mass of the H2O is 0.172 grams. And we're supposed to knock out the little subscripts and whole numbers. What's the empirical formula? All right. So it's going to start out similar to before. So we're going to focus on the carbon and then focus on the hydrogen. Okay. Let's see. So the mass of the carbon dioxide was 0.421 grams. We're going to use the molar mass of carbon dioxide, which is 1 mole of CO2 per 44.01 grams of CO2. Then we're going to recognize that you have 1 mole of carbon for every 1 mole of CO2. And that will give us moles of carbon. I can't remember, do I stop there? Round to 3 significant figures. So now, elements, we have carbon, hydrogen, and oxygen. Moles of carbon from the carbon dioxide, 0.00957. Right, we're going to do a similar thing then with the moles of hydrogen from the water, I think. Okay, so moles of hydrogen from the water, we use the mass of the water, and the sample was that we got after combustion was 0.172 grams H2O. Use the molar mass of H2O, so 1 mole H2O per 18.02 grams of H2O. Then, like you told me, we have 2 moles of hydrogen for every 1 mole of H2O. So that's the third term. 2 moles of H for 1 mole H2O. So we're left with units of moles of hydrogen. Round it only to 3 significant figures. It looks like this. So moles of hydrogen is 0.0191 moles. All right. So I mentioned there's going to be an extra step. That looks all the same for now. But we need to take these moles and get them to grams. See, basically, if I was drawing a picture, sorry for kind of writing behind you guys. So this sample has carbon, hydrogen, and oxygen in it. Okay? And we know the mass of the sample. Do you see where if I subtract the mass of the oxygen and the mass of the hydrogen, that is, did I say that right? No, I didn't. If we subtract the mass of the carbon and the mass of the hydrogen, that is equal to the mass of oxygen, sorry. And that's exactly what we're going to do. We're going to convert these masses. How do you go from moles to masses? The molar mass. Okay? So actually that's done right here. How do we know what the mass of carbon is? By taking these moles and using the 12.01 grams per mole. Okay? So we're going to piggyback on the moles we had, 0.00957 moles of carbon. Pick off the decimal number for carbon, 12.01 grams carbon per 1 mole of carbon. And there you go. Round to 3 significant figures. The mass of carbon in the sample that we burned must have been 0.115 grams of carbon. So we're ready, 0.115 grams for here. Mass of hydrogen, we're going to do similar. we're gonna use this mole of hydrogen, which is 0.0191 moles of hydrogen. And we're gonna use the decimal number for hydrogen, 1.008 grams of hydrogen per 1 mole of hydrogen. Rounded to 3 significant figures, that's the mass of hydrogen. 0.0192 grams of hydrogen. Cool. So, we're ready to go ahead and get, I know it just seems like an extra step, definitely an extra step. So like I said, we can knock out the mass of the oxygen if we take the original mass of the sample and subtract out the carbon and hydrogen, that leaves us the mass of the oxygen. So of course, in the original problem statement, the mass of the thing that we burned was 0.236 grams. So you take 0.236 minus 0.115 minus 0.0192. So remember, we don't do a lot of subtraction in chemistry, but if we do subtract, we have to round according to decimals. And fewest decimals we know is 3. So finally, we know the mass of our oxygen. And there are actually, I've seen more than one way to work this problem. This is the way I learned it and the way I'm going to teach it. But if you learned it another way, or go about it another way, but somehow we got to get relative moles of carbon, hydrogen, oxygen. So there's the grams of oxygen. Of course, we can get moles of oxygen now using the molar mass of oxygen. So then we'll go 0.102 grams of oxygen. Look up the decimal number for oxygen, which is 16.00. So we'll put 1 mole of oxygen over 16.00 grams of oxygen. And voila, we're ready for our third number up there. So here is that third number, relative moles, 0.00636 moles. So if you do like a table thing like that, to me it's kind of like a table, and you also have some other stuff going on. So it's kind of like, you know how an artist kind of looks at the whole picture, and some problems are like that. So then, of course, let's go ahead and finish this thought. I would make another column, and I would divide by the smallest. So it looks like the smallest is my oxygen. So I'm going to go ahead and divide everything by 0.00636. So 0.00957. Divided by 0.00636. I got 1.50. Oh, we got a halvesies going on. Okay, so this is, so you think another column? I think so, 1.50. And then 0.0191 divided by 0.00636. Oh, I got an even number, or a nice round number, 3.00. Okay, and then of course I'm kind of running out of room here, but this divided by itself is 1. So I need one more column. I'm going to multiply through by...
Just multiply by 2, couldn't you?
By 2, yep. Yep. You know, I'm into making sure that you show all of your work. So I'm going to keep that in mind. But so if we take 1.5 times 2, that gives us a nice round number of 3. 3 times 2, of course, gives us 6. And 1 times 2 gives us 2. Awesome. So it looks like we're ready to go ahead and knock out the empirical formula. So it looks like C3H6O2. That's it. So instead of the columns, it would look kind of like this, kind of the logic we looked at before. Again, you pick on what's there in the least number of moles, which is the oxygen. We know, relatively speaking, there's 1.50 moles of carbon for 1 mole of oxygen. We could scale that up by multiplying through by 2, and of course we get 3 moles of carbon per 2 moles of oxygen. And then we need to do the same thing with hydrogen and oxygen. Okay, so if you divide the 0.0191 moles of hydrogen by 0.00636 moles of oxygen, you get 3 moles of hydrogen for every 1 mole of oxygen. See, this is where it starts to hurt my brain. I'm like, okay, so but we need to scale that one up too. It's not too bad, I guess, either way. You come to the same conclusion. Okay, so that's the empirical formula.
Choo-choo.
All right. So like I said, we've just taken advantage of the fact that we could track the carbon by looking at the carbon dioxide. We could track the hydrogen by looking at the water. That same thought, actually you have a homework problem that's going to be due on Monday, has you tracking sulfur by sulfur dioxide that's generated. So you can do the same thing, okay? All right, so let's take a look at your assignment. Thanks. Only 4 problems. All right. So, for this one, again, it's a hydrocarbon. Read it closely. You will have either a hydrocarbon or a hydrocarbon with oxygen on your Unit 2 exam, or you'll have something even more creative, like something containing sulfur, and you can track the sulfur from the SO2 that's formed here in one of the problems that's assigned for Monday. This one's a little bit different. If you read through it a few times, they want you to say what the mass percent composition is, what the empirical formula is. That's what we've been doing. But they also want you to take the empirical formula all the way to the molecular formula,
Oh, cool.
using something that we did actually in part 2 with our weight percent problems. They basically give you the molecular weight, the weight of the molecule, which is that 106 AMUs, okay? So this is where one of the last things we're going to do is see how many repeating units, how many empirical formulas we need to make up for our one whole molecular formula. So, so to get the weight percents, there's more than one way to do this, but this is kind of how I did it. Forget it kind of went out of order. So you can, but if we focus on carbon first and then hydrogen, we can get the mass of carbon using carbon dioxide, the molar mass of carbon dioxide, and moles of carbon dioxide, the relationship between carbon and carbon dioxide to get to moles of carbon, and then the molar mass of carbon to get to grams of carbon. All right? Similar thing for hydrogen. Actually, we could do a similar thing for hydrogen and water, but actually you can see I wimped out and I just went back to the mass that was burned, and I said, well, dang, if I know the mass of carbon and everything else is hydrogen, I just did it by difference. So you could do either way there. And then, of course, weight percent are always going to be about the mass of the element divided by the total mass, and of course the total mass is 0.188 grams, okay, times 100%. Then B, you're ready to knock out the empirical formula like we just have been doing. You already have grams of the elements, so you can go to moles of those, okay, since you already kind of piggybacked from A to B. And relative moles then kind of distill it down to what the integer should be. That's the empirical formula. And then just to kind of remind you what we did in part 2 was to go all the way then, now that you have the empirical formula, to go to the molecular formula given the weight of the molecule, like up above. Basically, you're going to take how much the whole molecule weighs, which is, I said 109, really it's 106. So you're going to take how much the whole molecule weighs, 106 AMUs, and you're going to divide by the mass of just the repeating unit, the empirical formula. You should hopefully get a nice round number, And then you're basically going to scale up your empirical formula, okay, by multiplying through by that integer. So that'll be a good one. The next one, actually this one contains oxygen. They give the mass of the thing you burn. They give the mass of the carbon dioxide in the water. And again, you're supposed to come up with the weight percent of carbon, hydrogen, and oxygen. So do it similar to the last one. Speed this up a little bit. Okay. The thing that's different is that, I'm still back on A, the thing that's different is you can't get to oxygen, okay, straight off the bat. Basically, you have to get to carbon to hydrogen first, and then by difference, you subtract from your original mass, that 0.4039 grams of your sample that you burned, you subtract carbon and hydrogen to get to oxygen. All right, so that should work. This one is the one that actually has sulfur in it, carbon, hydrogen, and sulfur. So it's actually easier than carbon, hydrogen, and oxygen. Because in this case, all of the sulfur in the thing that you burn ends up as sulfur and sulfur dioxide. So it is, I think, easier. So you end up kind of doing what we've been doing here 3 times. Get the carbon from carbon dioxide, get the hydrogen from water, get the sulfur from sulfur dioxide. And then go ahead, I said, and kind of clean up things to get it into an integer. And that one, all you're supposed to do is the empirical formula. Then this one is a little different. It's alcohol. And in this case, they give you the mass of the alcohol, and you're supposed to say how much carbon dioxide and water would you get back. Definitely more than one way to skin this cat. I'd be tempted to balance it and make it into a regular stoichiometric calculation. I don't know. But I noticed in my notes that actually that isn't what I did. You can get the mass of the CO2 from using the mass of the sample you burned, converting it to moles using its molar mass, and then how many moles of carbon? Well, there's 4 moles of carbon for every mole of a compound. And once you have moles of carbon, recognize that you can get to moles of carbon dioxide from the carbon, and then you can actually then go from moles of carbon dioxide to grams of carbon dioxide using carbon dioxide's molar mass. Very similar thing with regard to the water. Focusing on, you have 10 moles of hydrogen per 1 mole of the compound, and in water, you're going to get 2 moles of hydrogen for every 1 mole H2O. So,
And then dance and sing.
yeah, just because I could. Okay, so that's it, and I'll go ahead and post those. But
So why don't they just write it as